In this last video of the semester, we're going to be looking at a concept called quadratics in form. And these are equations which might not be literally quadratic equations, but they can still be solved using quadratic methods. So a quadratic equation would say ax squared plus bx plus c equals 0. What we're going to be seeing is instead of just an x in these boxes, we'll see some other things in there that make the equation not necessarily quadratic, but looking at it in this format will make it appear quadratic, and so we can use quadratic methods to solve. So in this first example, excuse me, this is technically a quadratic. If I actually distributed to get rid of parentheses, I would see an x squared here. And while we can use different quadratic techniques to actually solve this, let's attempt doing a quadratics in form method on this so that when we have something that's not a literal quadratic equation, we can use this new technique to solve it. So what I want us to be able to see is, can we rewrite this equation just visually so it looks like this format, where a, b, and c are just the first, second, and third coefficients here. So let's see if we can just change the way we see this equation. Can we see it as something squared plus 5 times something plus 4 equals 0. So let's see it this way. Now in this particular example, the something that goes in the box turns out to just be those parentheses, the x minus 6. Now because x minus 6 is not just one simple letter, there's several letters involved, what I'm going to do is I'm going to give that stuff in the box a nickname. I'm going to call it u. Let's let u equal x minus 6. And so now everywhere I see that complicated, cluttered mess of x minus 6, I'm just going to say, hey, u. I'm going to call it u. And so now what I have, if u represents x minus 6, this now says u squared plus 5 times u plus 4 equals 0. And this is another quadratic equation, but this looks a lot simpler than the original one. What I can now do is I can solve this equation. It is a trinomial set to 0, so let's go ahead and use an x box to factor what multiplies to 4 and adds to 5. That's going to be 4 and 1. Notice when I'm factoring it, I'm using the letter u because that was the variable in this trinomial that I'm trying to factor. Now if something times something is 0, one of them's got to be 0. And so if u plus 4 equals 0, u must have been negative 4. And if u plus 1 is 0, then u must have been negative 1. Now this is where I have to be really careful. That's not the solution, because you know what? It's not about u. It was about the variable x to begin with. So here's where we have to be careful. Yes, we can simplify things by giving that nickname u, and we can find out what u is, but it wasn't about u. We have to go back to see what it means for the original variable x. So what I'm going to do is I'm going to take the statements I just got here. I said that u equals negative 4 or u equals negative 1. And I'm actually going to separate those out because now I've got two different equations that I'm going to be working on. I'm going to work on u equaling negative 4 and u equaling negative 1. But let's recall, what did u mean? We said u was a nickname for x minus 6. So this really says x minus 6 equals negative 4, or x minus 6 equals negative 1. And now here are two easy linear equations. If I add 6 to both sides, x is going to equal negative 4 plus 6 is 2. And then over here, x equals negative 1 plus 6 is 5. So I wind up with the solution x equals 2 or 5. Now, this is a lot of work for us to do for this particular example because it was technically a quadratic to begin with. The reason we're going through this new technique is that eventually we're going to be seeing examples that are not literally quadratic equations. We're going to look at quartic equations, we're going to look at equations with fraction exponents, and we want a technique that will work. This technique of thinking of this as something squared plus 5 times something, and then giving that stuff a nickname, that's going to help us simplify things down the road. Let's try another example where we again have a literal quadratic equation, see if we can use this new technique again, and then we'll extend that into other types of equations. Now, if you're not sure whether this truly was the solution, I would encourage you on your own to take this equation, try to distribute to get rid of parentheses, solve that quadratic, and see if you wind up with the same two answers, because you should. Let's do one more example with a literal quadratic, and then we'll open it up to some other types. Here's another example with a quadratic equation, but because of the way it's set up, where I see matching parentheses, it's trying to get me to notice that matching parenthesis, trying to get me to see that pattern so that I can try and write it as a quadratic in form. So let's see if we can rewrite this so that it says something squared. Now I'm going to want this to be equal to 0, so let's imagine moving this to the other side. It would be minus 9 times something plus 20 equals 0. So again, I've taken this 9 times x plus 2, I've imagined moving it to the left, subtracting it, so now it's minus 9. And imagine what goes in the boxes. It's the parentheses stuff. So in the box goes the parentheses stuff. And these technically say the exact same thing, but because we're seeing it in this light where these boxes match, since those boxes have lots of stuff in them and because they match, it might be beneficial for us to give that a nickname. So let's let u represent x plus 2, the stuff that was in the parentheses. So it's a nice nickname I can use. So now, when I see x plus 2 squared, I can just say that's u squared. So giving it a nickname, u squared minus 9. Again, instead of using all this stuff, we'll just say u. And then plus 20 equals 0. By using that nickname u, we've made the original equation just look a little bit more simplified. It looks a little bit easier because it doesn't have as much clutter. So let's now take that equation, factor it to solve. I see a trinomial on that left side. Let's see if we can factor, finding numbers which multiply to 20 and add to negative 9. And I'm seeing negative 4 and negative 5. I'm throwing them right into parentheses because there was nothing in front of the u squared. Now, if something times something is 0, one of those factors must be 0. If u minus 4 equals 0, then u would equal 4. And if u minus 5 equals 0, then u must equal 5. But again, it's not about u, right? This equation originally had x as the variable, and so while I know what u represents, u was just a nickname for x plus 2. So what this says now, instead of saying u equals 4 or u equals 5, I want to call upon its formal name rather than its nickname. So when I see u equals 4, what I'm really looking at is x plus 2 equals 4. Instead of u equals 5, I'm really looking at x plus 2 equals 5. And so now I've got these two linear equations. To solve for x, I'm just relocating the 2 to the other side by subtracting. So x equals 4 minus 2, which is 2. Over here, x equals 5 minus 2, which is 3. And so I get those two solutions, 2 or 3. And again, if you weren't sure whether this technique was working, you could take this quadratic, you could distribute to remove parentheses, and you could factor that quadratic equation. You'll wind up with the same solutions. And it would probably be a little less writing than what we've done here, but the point of showing you this technique is that this will not only work for this quadratic, it will work for things that are not quadratic, but that appear quadratic in their form. Let's take a look at an example that's not quadratic, it's actually quartic, but we'll see how to use this same technique to solve it. Here is a quartic equation. A quartic equation has a highest exponent of 4. It is not a quadratic whose highest exponent would be 2. However, this could be written to appear quadratic in form. So let's see how we might do that. How can we make this say something squared minus 13 times something plus 36 equals 0. So notice I've just taken the coefficients and dropped them in front here. But I want to know what would need to go in the boxes so that it actually said the same thing we had. The key is going to be looking to the middle. If this needs to say minus 13x squared and I have minus 13 blank, well, the blank must have x squared in it. Let's imagine putting that in the other box and just verify x squared squared really is x to the 4th. And so x squared is going to be in the box. Now that's not a quadratic again. This is a quartic. But if I give x squared a nickname like u, then this is going to look quadratic. Let's let u equal x squared. So every time I see that combination of symbols, x squared, I'm just going to say u. So now instead of saying x squared squared, I'm going to say u squared. Minus 13 times x squared is just minus 13u. And then plus 36 equals 0. So the original equation was quartic, but by giving this a nickname, I now have an equation that is quadratic. So I can solve this using my quadratic techniques such as factoring. What multiplies to 36 and adds to negative 13? I'm seeing negative 9 and negative 4. Notice when I'm factoring here, I'm using the letter u because I'm factoring a trinomial with u in it. And when I solve this, I'm finding what u equals. If u minus 9 or u minus 4 must equal 0 to multiply to 0, then u must be either 9 or 4. But it's not about u. We have to find the original variable, which was x. And so I'll go back to the side here where u equaled 9 or u equaled 4. Let's now go back in and instead of writing the nickname u, let's write the formal name, which was x squared. So this would say x squared equals 9 or x squared equals 4. And think about how we would get x by itself. If there's a square attached to it, I can detach it with a square root. Just remember that when the square root undoes the square and the square disappears from the left, remember there's a plus or minus that appears on the right. The square root of 9 gives me 3. Over here, again, the square root undoes the square, but when the square disappears, I need a plus or minus, and the square root of 4 is 2. So pulling all of this together, I have several different answers here. I have positive 3 and negative 3. I have positive 2 and negative 2. That's 4 different solutions, which I actually expect because it was a degree 4 quartic equation. Now I went ahead and wrote out all 4 answers because I just wanted to emphasize that there were 4, but you could certainly use plus or minus symbols to help make this easier to read. So you could just say plus or minus 3, comma, plus or minus 2. We'll do that in the next example. So let's do one more with a quartic where again, we have a degree 4 and we create a nickname for that x squared. Let's see it happen again. Here's another quartic equation. Notice this one's not set equal to 0. I am going to want to see it set equal to 0. So let's imagine moving that 3 by subtraction. But again, we're looking for it to say something squared. In this case, plus 2 times something. And then if the 3 relocates, we'll have minus 3 equals 0. Now I do want to make a quick comment here in terms of which one has the square, which one doesn't. The square is going to be on the box for the term that has the higher exponent. If there's no square on the box, that's the lower exponent. And then the constant doesn't have a box at all. So high exponent gets the square, low exponent gets a plain box, and the constant is still just a constant with no box. But what's going to have to go in the box to make these equivalent? Again, look to the middle. If I want the middle to say plus 2x squared and it says plus 2 blank, x squared must be in the blank. And these boxes are going to match. And x squared squared is x to the 4th. So again, when I have a quartic equation, my nickname u is always going to represent x squared. So in the examples where I had the parentheses, it was the parentheses that became the u. In these examples with the quartic degree 4, the u is going to represent the x squared every time. So now I can rewrite this equation. Instead of x squared squared, I'll just say u squared. Instead of plus 2x squared, I'll say plus 2u. And then I've got minus 3 equals 0. Again, I've reduced this from a quartic to now it appears as a quadratic. I can now solve this by factoring. So what numbers multiply to negative 3 and add to 2? I'm seeing positive 3 and negative 1. Again, notice for right now, I'm factoring with that nickname u. And I'm finding that u equals negative 3 or 1. But it's not about u. It was about the original variable x. So when I see u equals negative 3 or u equals 1 down here, I now break those apart and give it, instead of the nickname, I give it the formal name. So instead of u equals, I want to see x squared equals. Again, instead of u, I'll see that formal name x squared. Now to get x by itself, we have to remove that square. We can remove the square using the square root symbol. But remember, as soon as the square disappears from the left, you're going to need that plus or minus on the right. Now the square root of negative 3 is I square root of 3. Again, as soon as the square disappears, we need a plus or minus. The square root of 1 is just 1. And so here I have plus or minus I square root of 3. That's two imaginary numbers. I have positive I square root of 3 and negative I square root of 3. I also have positive and negative 1. That's 4 separate answers. 2 here and 2 there. 4 separate answers that I'm getting, which I expect for a degree 4 quartic equation. So again, for the quartic equations, your nickname for u, it's going to represent x squared every time. Let's look at one more type, where this time we're going to see fraction exponents. But again, we'll reduce it and simplify it using the nickname u, and we'll make it look like a quadratic in form. So here's an example where we have fraction exponents. It looks pretty nasty, but it's written in a format that can be seen and viewed as a quadratic in form. Let's see how we can do that. I want to be able to view this equation as something squared minus 3 times something minus 10 equals 0. So again, I'm just pulling down my coefficients. The big exponent, the one that's higher than the other, the big exponent will go with the square. The smaller exponent has no square on it. And the 10, the constant, just stays a constant with no box. But we need to figure out what goes in the box. Again, the middle is usually the easiest place to see it. The middle should say minus 3 x to the 1/3. I see minus 3 blank. So the blank must be x to the 1/3. And these boxes ought to match. So this should also say x to the 1/3. But let's just make sure. If I took x to the 1/3 and squared it, what do I get? Well, when I raise an exponent to an exponent, I multiply. 1/3 times 2 is 2/3. So this does match the original. But x to the 1/3 is a messy thing to have to keep referring to, so let's give it a nickname. Let's let u represent x to the 1/3. So every time I read x to the 1/3, I can just think u every time. So instead of x to the 1/3 squared, I'll say u squared. Instead of minus 3x to the 1/3, I'll think minus 3u. And then minus 10 equals 0. This is a much simpler looking equation. Instead of all these fraction exponents, it's now a nice clean quadratic. And again, if it's set to 0, I can start by factoring. I'm looking for numbers which multiply to -10 and add to -3. I'm seeing -5 and +2. Again, right now, I'm using the letter U. I'm thinking in terms of nicknames right now while I solve this. And so now I get two solutions for that letter U, for that nickname. If U minus 5 is 0, then U must be 5. If U plus 2 is 0, then U must be -2. But it's not about U. It was about the original variable, x. So now what I do is I go back and I say, instead of talking about the nickname, instead of telling you what U equals, let's now go back to the formal name. Before we get to the formal name though, I just want to have us recall what this weird notation actually means. When I see a fraction exponent, that's code for something. It's a radical. Remember the type of root, remember where roots grow down and the denominator is down, that tells us this is a cube root. So x to the 1/3 is actually the cube root of x. So it's been a little while since we've seen that, but that's all that fraction exponent really means. So when I said u was a nickname for x to the 1/3, I could actually say it's the cube root of x, if that's an easier way to look at it. So when I say u equals 5, I can say that really means the cube root of x equals 5, because that's what u meant. Instead of u equals -2, I can say the cube root of x equals -2. And if I'm thinking of it as a cube root, this is going to work very similarly to when we were solving radical equations with square roots. To undo a square root, we had to square both sides. Well, to undo a cube root, we're going to cube both sides. So if I cube the cube root, it will go away. On the left side, the cube undoes the cube root and I'm left with x. On the right, 5 cubed is 125. Again, the cube root cubed gives me just x. -2 cubed is -2 times -2, which is 4, times another -2, which is -8. So I wind up with two solutions here, 125 and -8. Let's try just one last example for the whole semester. We'll do another one just like this, which again has exponents that are fractions. Those fraction exponents really are code for, hey, there's a root of some kind. We're going to let u represent that root. And when we find our solutions for u, we'll turn it back around to talk about x. Let's give it one more try. So one more time, we want to rewrite this equation so it appears as a quadratic in form so that we can solve it more easily. So can we make it look like this? So remember, the higher exponent is the box with the square. So this guy's my box with a square. Here's the something squared. Now I'm going to plan on moving these terms back to the left. They will both get subtracted. So I'll have -2, and then the smaller exponent is the plain box. And then this constant, when he moves, becomes -8. And now it's set to 0. All right, what goes in the box? Look to the middle. It should have a 2x to the 1/3. I have 2 blank. So I need x to the 1/3 in the box. Again, x to the 1/3 squared, I would multiply those exponents to get x to the 2/3, so this is looking good. Instead of saying x to the 1/3, x to the 1/3, I'm going to give it a nickname. I'm going to let u be a nickname for x to the 1/3. So every time I see x to the 1/3, I'll just say u. So here's u squared. minus 2 times u minus 8 equals 0. And now I've taken an equation which looked kind of intimidating at first, and I've made it look like a nice clean quadratic. And I can factor this trinomial to solve. What multiplies to negative 8 and adds to negative 2? I'm seeing negative 4 and positive 2. And so what does u equal? If u minus 4 is 1, or if u minus 4 is 0, then u must be 4. And if u plus 2 is 0, then u must be negative 2. But I'm going to say it one more time. It's not about u. It was about the original variable, x. So where I saw that u equaled 4, or u equaled negative 2, it wasn't about that nickname, it was about the formal name originally. And while I gave the nickname for x to the 1/3, remember what x to the 1/3 means. It's the cube root of x. And if we spell it out that way, it might be easier for us to solve over here. So u was the nickname, the formal name is actually the cube root of x. So the cube root of x is 4, or the cube root of x is negative 2. And now to get the x by itself, to remove the cube root, we will need to cube both sides. So let's cube the left and the right for both of these equations to make the cube root disappear. Cube undoes the cube root, I get x. 4 cubed is going to give me 64. Again, the cube undoes the cube root. And negative 2 cubed, we saw this last time, gives us again negative 8. So again, I'm getting two solutions. In this case, I'm getting 64 and negative 8. So you'll see several problems in the example, some with parentheses, some that are quartics with degree 4, and some which have these fraction exponents, but I'll tell you what, they're all solved the exact same way. So try and figure out how to fill in the boxes so that you can give a nickname to the box stuff. Work through the nickname to solve, and then bring the formal name back to give your final answer. That's it for the whole semester. You guys have done a great job.